Welcome to this video. We are going to be talking even more about related rates, going over some kind of strategies and processes that you can use to solve these kinds of problems, and doing a few more examples. And so I wanted to make several videos about related rates because it tends to be the topic that trips calc students up the most, but I really think that if you kind of come up with a process, even if it's not this process, that really works for you and it's a uniform process that you can stick to every single time, I really do think that that is going to help you do related rates problems. So you can see here that I've put kind of some strategies and tips that I use when I'm doing these problems. And right over here where it says related rates key steps, what I did here is I kind of took a related rates problem and broke it down into its most fundamental pieces in terms of the steps you use. So obviously each of these steps, 1, 2, 3, 4, is going to have little sub-steps and things that go into them, but if you break a related rates problem down to kind of its just core elements, this is what you're doing. So when you're given a problem, the first thing you want to do is organize your information, sort through everything that they've told you, and put some labels on them. And then you're going to write the relevant equation. So every single time you're doing a related rates problem, there's going to be some equation that relates the physical quantities in question, and that is the equation that you need to figure out, and oftentimes that's the hardest part, is figuring out which equation is the relevant one. So that's a really big piece. It's just, what equation am I going to even be using for this problem? And then once you figure that out, you differentiate it and then plug and chug, which means that you plug all the values you know into the differentiated equation and you solve for the missing piece. So it sounds easy, right, when you break it into these steps, but hopefully when you see me adhere to these steps in a few worked examples, it'll make more sense. And I also wanted to go over some tips that I have for doing these problems. I will also put these tips down below. They're just kind of key things that I've seen students make mistakes on a lot, so I wanted to really highlight them. The first one is that you're almost always differentiating with respect to time, so every other letter that shows up in the equation needs to be differentiated like a function. So in the last video we had an equation that was the area of a circle, and there are two quantities in that equation. There are area and radius, and neither of those were the independent variables. So when we took the derivative, we had to treat them like a function and use chain rule. That is very commonly missed, so make sure you're really diligent about that. The next one is make it clear on your paper exactly what you're trying to solve for. Either like write it in the top corner of your paper or something, put a box around it, write it out in words or symbols, whatever works for you, but just make it super clear what you're trying to solve for, because especially when you get halfway through a problem, it's really easy to kind of just get lost and forget what even you're trying to do. So write it down somewhere so you can always look at it and you don't forget what your end goal is. Another tip is to use differential notation as much as possible. What I mean by that is I'm talking like the dH over dt notation, because I think that really helps remind you when you're dealing with a derivative, because that gets forgotten a lot. And also label everything, and that goes along with drawing a picture. When I say draw a picture every single time, I'm serious, really. Even if you don't think it's necessary, you think you got it, you can do it in your head, just draw a picture every single time. It's going to help you avoid so many small dumb mistakes, and label everything on that picture. If you have a triangle and they didn't give you labels for it, come up with labels. Call one side A and B, or call one side Z and F. It doesn't matter, just label everything and be super consistent. And then lastly, some equations that come up really commonly in these problems are Pythagorean Theorem, similar triangles, the area/volume of a circle, and volume of a cone. This is not an exhaustive list, but these are just some of the more common equations that come up. So make sure you just kind of remember what they are. I think a lot of times students, they are trying to do step 2 over here, write the irrelevant equation, and they're really struggling, and then someone goes, well, what about using similar triangles, for example? And they just go, oh, I completely forgot that's a thing. So kind of just keeping these in the back of your mind and knowing that they might come up in a related rates problem might really help you with the writing the relevant equation step. So hopefully you got all those tips down. Again, I will leave them in the description for this video. So we're now going to look at an example and try to apply this process to this example. So here we have a 25-foot long ladder that is leaning against a wall and sliding toward the floor. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? And so, again, it's really easy to get overwhelmed by these problems because they just kind of threw us a lot of information. And do not try to just sort through all of this in your head. It is extremely difficult and probably will leave you feeling a little overwhelmed. So try to stick to a process again to organize all your information. It will really help. So looking at all this, I'm like, okay, there's a lot going on. I can't think about all that in my head at once. So I'm going to start by drawing a picture and organizing my information. So we have a 25-foot ladder that is leaning against a wall. Okay, so we'll say that the wall is right here and the ladder is leaning against it. So that means the ladder is at some angle like this, and then that is the ground. So there's my ladder, this diagonal piece, and we know that it's 25 feet long. So I'm going to label that as 25 feet. Okay. And so it's leaning against a wall and sliding toward the floor. So what they mean by that is that the top of the ladder right here that's touching the wall is sliding down. So this ladder is sliding down the wall. And then if the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top? Okay, so now we have this other bit of information that we need to do something with, this 15 feet per second. So before I actually go any further, what I'm going to do is I'm going to label my picture, right? So I have this 25-foot length, and so I'll just call that L because it's our ladder. So that is going to be L. And then I want to label the floor right here and this vertical height right here. So it doesn't matter what letters you pick. So I'm just going to pick Y to represent this vertical height from the top of the ladder to the bottom to the ground. And then X is going to represent the length from the wall to the base of the ladder. Okay, so now we know that the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second. So when they talk about the foot of the ladder sliding away from the base of the wall, which length are they talking about? Are they talking about X or are they talking about Y? And so hopefully you'd say that they're talking about X because they're saying that the bottom of the ladder here is sliding away from the base of the wall. So they're talking about this X value right here. They're saying it's sliding away at a rate of 15 feet per second. So immediately that word rate should jump out to you. So that means this quantity, 15, is going to be some sort of derivative. It's a rate of change. And a rate of change of what? Well, we just decided that they were referring to this horizontal length X here. So if they're referring to this length, then the rate of change would be dx dt. Because we're talking about how does this length X change with respect to time. Remember, in these related rates problems, it's almost always going to be with respect to time. So be really careful of that. So we're saying that the rate of change of this horizontal length, the base, is 15. And another way you could have figured out that it was a rate of change is by looking at the units on it. It was 15 feet per second, and feet per second is a rate, right? Because we have something per something. Okay, so we kind of came up with some notation for this 15 value, and I super suggest you use this differential notation, dx dt, instead of just writing like the rate of change is 15, just because dx dt is much more specific, and when you differentiate your relevant equation, it is going to be super helpful that you wrote it this way, and you'll see why. Okay, so we're still in the part of organizing our info and drawing a picture. So we have a good picture drawn, and we have this quantity labeled. What else did they give us? They said that they want to know how fast is the top of the ladder sliding down the wall. Okay, when they talk about the top of the ladder sliding down the wall, what quantity are they referring to? What letter are they referring to in our picture? And so hopefully you'd say Y, because they're talking about the top of the ladder going down the wall. So that is going to be this vertical distance here. So they want to know the rate of change of Y. So if we wanted to use differential notation to represent that, we would say dy over dt, right? Because this tells us what is the rate of change of this vertical quantity y with respect to time. And so the reason I wrote it in blue, and I'm now going to put a nice box around it, is because this is our end goal. This is what we are trying to find. So just going to star it and make it super obvious. It'd be super helpful that you write what you're trying to find, because again, it's easy to get lost in all the information. Okay, so this is what we are trying to figure out, dy dt. And what's the last bit of information that's been given to us? They want to know what dy dt is when the top of the ladder is 7 feet from the ground. Okay, so when one of these quantities, either y or x, is equal to 7. So which one do we think it would be? It's talking about the top of the ladder being 7 feet from the ground. So hopefully you'd say that that represents a quantity y, right? Because they're talking about the top of the ladder to the ground, that distance. So that's a vertical distance, so that's going to represent y. So at the moment in question, y is going to be equal to 7, because that is that vertical distance. So this is what I mean by organizing our information. I've drawn our picture, I've labeled it, and then I've written everything that they've given us using the notation from my picture. Super important. Do not use different letters. Like, stick to the same letters, be consistent. And then I made it really, really obvious what we were trying to figure out, dy dt. Okay, so all I did was just organize my information, make it look neat. Now the next thing we need to do is write the relevant equation. So I'm going to do this in a different color because it's super important. Okay, so when I say relevant equation, I mean an equation that relates all of the physical quantities that we are trying to figure out. So let's look at this. Our picture over here, we have this vertical distance y, we have this horizontal distance x, and then we have this diagonal distance that's 25 feet. It's the length of the ladder. What does the shape that I drew kind of look like? And so hopefully you'd say that this is a right triangle, right? I could put a little angle there. So we have a right triangle drawn. Now, is there any equation that relates all three sides of a right triangle? And so hopefully you'd say, well, that's just the Pythagorean theorem, right? The Pythagorean theorem tells us a squared plus b squared equals c squared. So that involves all three sides. So that is going to be my relevant equation. But instead of using a, b, and c, you should stick to the labels you have given your picture. So our relevant equation then, using the labels that I've put on here, is going to be x squared plus y squared equals the hypotenuse squared, right? And do we know what the hypotenuse is? Yeah, it's 25 feet. So we can just say 25 squared. And the reason I didn't have to put some variable in here is because we know that the ladder has length 25 feet. And throughout this problem, is the length of the ladder going to change? Well, no. Even if the ladder is sliding down the wall, it's not going to magically change its length. So that's why I can just put a number out here, because I know that that is going to always be 25 feet, no matter what. So that's why I could just throw 25 right in there. So this is our relevant equation that we've written, because it relates all the information that we've been given. It relates the length of the ladder, the vertical height, and the horizontal height. So now we have our relevant equation and we want to differentiate it. That is the next step. And so remember, we are differentiating with respect to time. Super, super important. So let's go through this piece by piece. So we want to take the derivative of x squared with respect to time. So x is not the independent variable. So we need to treat it like a function and use chain rule. So if we take the derivative of x squared using chain rule, we're going to have 2x to the first. So I took the derivative of the outside, the squared piece. I kept x the same. And then chain rule says we need to multiply by the derivative of the inside. And x is our inside function. So the derivative of x is going to be dx dt. Because again, t is the independent variable that we are differentiating with respect to. And so now we need to take the derivative of y squared. Again, y is also a function, so we need to use the same process that we used here. So if we take the derivative of y squared, treating y like a function, we're going to use chain rule. So we're going to have 2y to the first, and then we need to multiply that by the derivative of the inside, by the derivative of y. And the derivative of y is going to be dy dt. And that is all equal to, now we need to take the derivative of 25 squared. And I don't know what 25 squared is, but luckily I don't need to know, because whatever 25 squared is just going to be a number. And the derivative of any number is just 0. So that works out really well. Okay, so now we have differentiated this, and we were really careful and made sure that we treated both x and y as functions. So we have finished step 3. And so now we just need to plug and chug, right? So we can throw all the information that we know in here. So we have 2, and then we need to multiply 2 by x. Do we know what x is, though? Let's go back to the information that we wrote over here. We know the length of the ladder is 25 feet. We know dx dt is 15. We know y is 7. But it doesn't look like we have x anywhere over here, right? So we actually need to figure out what x is. And so it's pretty common that you go through the differentiation process and then you realize, oh, there's still one thing that I need to figure out. I still don't know what x is. And so you can figure out x in the beginning if it's super obvious to you that you needed to figure x out right away. For me, it's not really obvious, so I just kind of wait until I get to my final equation and I just look at each piece and go, oh, do I know what that is? Can I figure it out? Oh, I can. Sweet, let's do it. So we need to figure out what x is. Okay, so how are we going to figure that out? Well, we know that the length of the ladder is always 25, that never changes. And we know that the moment that we're solving this problem for, y is 7. So if I'm going to redraw that triangle. The hypotenuse of this triangle is always 25. At the moment in question, y is 7. So can I figure out x? Well, sure. I can just use the Pythagorean Theorem again to figure out x. So x squared plus 7 squared is going to be equal to 25 squared. And now you just need to do a little bit of algebra and solve that for x. And so if you were to work through that and do all the algebra, hopefully you will get that x is equal to 24. So we just figured x out just by using Pythagorean Theorem. And again, I think it's easier to get to this equation and then go back and figure stuff out if you need to, because at least to me it's not super obvious that we needed to know what x was. But now we do know what x is, so we know that x is equal to 24, so we can substitute that in here. So we're going to have 2 times 24, and then that needs to be multiplied by dx dt. And do we know what dx dt is? Well, yeah, look we have it labeled right here. Dx dt is 15. So hopefully you now see why I really, really encourage you to use differential notation at the very beginning, because if you have it labeled as dx dt, then when you have dx dt in this equation here, it's really easy to be like, oh, look I have dx dt already labeled, it's 15, boom. If you didn't have it labeled like that and you had 15 labeled like with words, it's not just as obvious that 15 is what gets plugged in for dx dt. So as much as possible, I really encourage you to use that differential notation and get good at it, because then when it comes to just plugging stuff in, you're like, boom, it's right there, 15, we got it. Okay, and so now we need to add, and then we're going to have 2 times y, and again, we have y labeled right here, y is 7, and then times dy dt. Do we know what dy dt is? Well, no, because look right here in blue, that is what we are trying to solve for. So we can leave dy dt as just itself, because that is exactly what we are trying to figure out. And this is still all equal to 0. So now hopefully you see we've plugged in all of the relevant information, and now this is just algebra. There's only one unknown, dy dt. That's exactly what we wanted to figure out. So we just need to get dy dt by itself, do some algebra. So if you work this out, 2 times 24 times 15 is going to be 720, and then 2 times 7 is going to be 14, dy dt, and that's all equal to 0. And so now if we want to get dy dt by itself, we're going to subtract 720 from both sides. So I'm going to go up here. So if we subtract 720 from both sides, we're going to have 14 dy dt equals negative 720. And then the last thing to do is just divide both sides by 14. So dy dt is going to equal negative 51 point, and I'll just round to 1 decimal place, 4. For the AP test, you should round to 4 decimal places to be sure, especially on the FRQ, but for here, since I'm running out of room, I'm just going to round to 1 decimal place. So there it is, our answer. That's exactly what we were trying to solve for. dy dt equals negative 51.4. And now units are super, super important. Don't forget that. So what should the units on this be? Well, we know it's dy dt, so that means it's a rate of change of y with respect to t. So to figure out the units, we just need to figure out the y units and divide them by the t units. So what I mean by the y units is this vertical length over here is y. How did we measure distance in this problem? And it looks like feet, right? Like here they said 25 foot, here they said feet, here they said feet. So it looks like we're measuring distance in feet. So that means our y units are going to be feet per, and then how are we measuring time? And it looks like right here they told us feet per second. So we're measuring time in seconds. So our answer, dy dt, is equal to negative 51.4 feet per second. And so now you might be noticing that we have a negative over here, and that might be kind of strange. You might be going, oh, did we do it wrong? Did I do it wrong if I got a negative? And no, sometimes you might get a negative, and that's okay. And so let's think about why that makes sense. This means that the vertical distance y is getting smaller with respect to time. It's decreasing. And does that make sense based on our picture over here? Well, yeah, if y is this vertical distance and the ladder is slipping down the wall, it's falling down, it makes sense that this vertical distance is going to get smaller. So that's why it's negative. If this value dy dt over here were positive, that would mean the ladder would be going up the wall, which makes a little less sense. So it's really important that you kind of check, especially the sign on your final answer, you kind of check that against your picture and go, does that make sense? Because more often than not, when you're doing these problems, they should make like actual physics sense. So it's good to think about that and just double check. So hopefully, even though that was a lot of math, you can kind of see how just following these basic steps and trying to just do it piece by piece hopefully is helpful. And again, whatever process you come up with, even if it's not this one, try really hard to stick to it. I think that would be the best thing. So now we're going to try and use this process again for another problem, and this problem is a bit trickier, so the difficulty's been upped a little bit, but hopefully you'll see that we can kind of still use the same basic steps. So in this problem, we have a spherical balloon that is expanding at a rate of 60 pi inches cubed per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? So the very first thing I would always recommend you do with these problems is draw a picture. And so it'll be a bit hard to draw a three-dimensional balloon. So I'm just going to draw a circle and pretend like that's a three-dimensional sphere. And so we have this balloon and it is expanding. So it is getting bigger. So I like to draw just kind of a little arrow like that to remind myself that this is getting bigger. And it is expanding at a rate of 60 pi inches cubed per second. Okay, so that's the first bit of information that they've given us, is the 60 pi. So if we wanted, we know first of all that this is a rate, right? Because we have inches cubed per second. So this is a rate of change, or a derivative. So I want to write this in differential notation. So how would I do that? Well, since it's a related rates problem, and because you see seconds right here, we immediately know that we're differentiating with respect to time. So I already know that what's going to be on the bottom is going to be dt. But what am I taking the rate of change of? What is it? What physical quantity is changing? Well, it says that the balloon is expanding at a rate of 60 pi inches cubed. So this is your key to figure out what physical quantity is expanding. Inches cubed. So if we cube our units, what does that mean? That means we are dealing with volume if we cube units. And if we're dealing with area, then we square them. So we immediately know that when they say this balloon is expanding, they're talking about a rate of change of volume because of the units that they used. So we are talking about dv dt, the rate of change of the volume of this sphere. And we know it's going to be positive because this balloon is expanding. If the balloon was shrinking, it should be negative. But it's positive because it's expanding, and it's expanding at exactly 60 pi. So dv dt is 60 pi. Okay, what else do we know? Well, let's see. Now they want us to figure out how fast the surface area of the balloon is expanding. Okay, so that right there is what we are trying to figure out. This is our key. So surface area of the balloon. So how would we write that with differential notation? Well, first, let's come up with a letter that is going to represent surface area. So I'm going to say A is surface area. I know A usually stands for just regular area, but just for simplicity's sake, A is going to be surface area. So if we're talking about the rate of change of surface area, well, that's going to be dA dt, right? So the rate of change of surface area with respect to time. And this is what we are trying to figure out. They're asking us what this quantity is. So that's why it's going to get starred. This is our end goal. Okay, and then what's the last bit of information that they've given us? It looks like they told us that the radius of the balloon at the moment in question is 4 inches. So I'm going to use R to represent radius, and that is 4 inches. Okay, so we've organized all of our information. We kind of have an idea of what's going on. So now we want to write the relevant equation. So what is it? It's kind of helpful to look at your end goal when writing this. And our end goal is to figure out dA dt. Our end goal is to figure out the rate of change of surface area. So if we're going to do that, we need to have an equation that has surface area in it, right? How are we going to figure out the rate of change of surface area if our equation doesn't even have surface area in it? So our relevant equation then is going to be the surface area of a sphere. And so this is an equation that you may not remember. I honestly don't really remember it, but it'll be good to know for the AP test. And so the surface area of a sphere is 4 pi r squared. So that is just the surface area of a sphere. Okay, so this is our relevant equation because it involves the two quantities that we're dealing with. We're dealing with surface area and we're dealing with the radius, right? So now we have a relevant equation and we want to differentiate it. So we are going to take the derivative of this with respect to time, almost always. So piece by piece, the derivative of A, our surface area, with respect to time is going to be dA dt, right? Because A is a function. And that is all going to be equal to, when we take the derivative of 4 pi r squared, well, 4 pi is just a constant. So whenever we have a constant being multiplied by a function and we're differentiating, the constant is just along for the ride. So that 4 pi is just going to hang out. And now we need to take the derivative of r squared. So we're going to use chain rule here because r is a function. So the derivative of r squared is going to be 2r to the first times the derivative of the inside, which is dr dt. Okay, so now we're getting somewhere, right? We wanted to figure out what dA dt is, and hey, look, we have dA dt in our expression right there. So that's how we kind of know we're on the right track. And so now we're to the plug and chug stage, right? So we're trying to figure out dA dt, so that'll stay like that. 4 pi is just a constant. 2 is also a constant. We know what r is, right? We have r labeled over here as 4. But we don't know dr dt, do we? That is kind of what makes this problem the tricky one. So we don't know this quantity dr dt. We don't have it labeled over here. So we have to go about figuring it out a different way. In the previous example, we didn't know what x was, so we used the Pythagorean Theorem. So we're going to have to do a bit of a similar thing here, but it is kind of tricky. So again, this is just knowing that this is the next step you would do is just a little bit practice and getting really familiar with these problems. So okay, we don't know what dr dt is. What's the other bit of information that they gave us that we haven't used yet? And that is this dv dt equals 60 pi. So if you're stuck and you have a quantity you don't know and you're trying to figure out how to find it, look at any information that you haven't used yet. That should be kind of suspicious to you because almost always they're going to give you information for a reason. So okay, we haven't used this 60 pi yet, and this represents the rate of change of volume. So over here, I'm just going to write the equation for the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. So you might be wondering why I did that. Well, okay, so just bear with me for a second. If I were to take the derivative of this volume equation, so I were to take the derivative of this with respect to t, what would I get? Well, over here on the left-hand side, when I took the derivative of v, I'm going to get dv over dt, and then the 4/3 pi is just going to hang out front. And then when I take the derivative of r cubed, I'm going to get 3r squared times dr over dt. And so you might be wondering why I did this. Well, looking at this equation, do we know what dv dt is? Do we have a value for that? Well, yeah, we labeled it right over here. dv dt is 60 pi. And then do we have a value for r? Do we know what r is? Well, yeah, right here. We know that r is equal to 4. So if we were to plug dv dt and r into this equation, the only unknown would be dr dt. And that's what our whole problem over here in the surface area equation was, right? We didn't know what dr dt is. But if we use the volume equation and differentiate the volume equation, we can solve for dr dt and then plug it in there. So that was their kind of sneaky way of trying to get you to have to use two equations. Is they purposely didn't tell you dr dt, but did tell you dv dt, so you would have to go use the volume equation, plug in dv dt, and solve for dr dt. So let's do that. So we know dv dt is 60 pi, right? So we know 60 pi is going to be equal to 4/3 pi times 3r, what we know is 4, so we're going to have 4 times 4 squared, and then that is all times dr dt. So now we should be able to just solve for dr dt using a bit of algebra, just get dr dt by itself. So I'm not going to go through that manually step by step, but because you should know that algebra, but from here we would just have to get dr dt by itself. And so if you were to do that, you would find that dr dt is equal to 15/16. So that's perfect because we were stuck. We didn't know dr dt, but we just figured it out using volume, so we can plug it in there and finish this off. So we still don't know dA dt, but that's all equal to 4 pi 2. Do we know what r is? Yeah, r is 4, so we can plug that in. And now, do we know what dr dt is? Yeah, dr dt is 15/16. So now look at this. This is a pretty straightforward algebraic equation. dA dt, which is what we were trying to figure out, is just equal to 4 pi times 2 times 4 times 15/16. So all you gotta do is throw that in your calculator, and that is going to be dA dt. So if you were to do that and just type that in your calculator, you would get 30 pi. So dA dt is equal to 30 pi. And again, you want to make sure that you are using units. So let's think about what the units would be. So A represents surface area. And how do we measure surface area? Well, if volume was measured in inches cubed, then surface area should be measured in inches squared, right? And then how are we measuring time? Well, up here, our units were inches cubed per second. So that means we are measuring time in seconds. So dA dt is equal to 30 pi inches squared per second. And that is our final answer, 30 pi inches squared per second. So this problem had a bit of a twist to it because you didn't know what dr dt is, but that is common, that usually once you differentiate your relevant equation and you plug stuff in, you end up with one missing piece. So you might have to kind of do a little side quest here and write another equation to find that missing piece. But hopefully these steps, though, will still kind of help guide you through the process, right? We started by just organizing our information, making it super clear what we were trying to find. We wrote our relevant equation, which was this A equals 4 pi r squared. We took the derivative of it, and then we plugged in everything that we knew. And in the case of this one, dr dt, we just went and solved for it. So really, related rates problems, I know, can seem kind of daunting, but it is kind of the same process at its core. So again, just doing lots and lots of practice. Even if you don't like it, practice is what's going to make you really good at them. And who knows, maybe if you do a lot of practice, you'll end up liking them. So hopefully this video is helpful. If you have any related rates problems that you've seen in your classes that you would love to see a video on, please leave those in the comments, and don't forget to subscribe.